So hello all, thank you for being here. I'm Timos Ampelikiotis. Today I want to present you the Virtual-Loopback technology, which also has been presented in the previous ALS in Japan, and focus more on the performance benchmarks and optimizations that we did since the last ALS. A bit about of myself. I work on virtual open systems as an engineer on embedded systems and virtualization technologies, and I was the main developer of this design. The presentation includes three main parts. We will see the index in more details later, but just have in mind that we are going to see the description of the design, a brief overview of that, the optimization and benchmark, which is the core part of the presentation, and proposed features for 2023 AGL. And a small note on my side here, it's that this work has been received funding from the Horizon Europe program, and specifically the Aero project. Now a bit about the discussion index. We will see, as we said, a brief overview of the Virtual-Loopback, the history and the current status of the project, competitive technologies, benchmarks between them and Virtual-Loopback, the proposed features, and the conclusion. Let's get into that. So, what is Virtual-Loopback? Virtual-Loopback, as a title, it is a hardware abstraction layer for non-hypervisor environments based on Virtio, which means basically that it tries to bridge these Virtio drivers with user space components as VIOS user devices, for example. Now, benefits of this design or approach, it's that existing user space implementations, applications that was created to use Virtio drivers can be reused in hypervisor or non-hypervisor environments without any change. Hypervisors that supports already Virtio and VIOS user open standards are fully compliant with this technology because this technology didn't change anything about the Virtio or VIOS technologies. The data that are exposed from the Virtio drivers are directly mapped into the user space, so there is no copy, and this means that we have a bit of higher performance than the VIOS user case in Chemo, for example. Now, because the components of this technology, the hosting user space, the kerneling user space components are fully compliant with these standards, guarantees the openness and stability. A brief overview, and we will dive in the specific components in the next slides. So, as we already said, we are trying to bridge Virtio drivers with the VIOS user devices. This is done basically with one kernel space component called Virtual-Loopback transport driver, or Virtual-Loopback, whatever you call it, and the adapter. The adapter, it's a user space component, which is basically manages to. First of all, let me talk a bit about the kernel because it's a bit more easier. Now, the kernel driver has the main role to take all the communication from the Virtio drivers, block, RNG, input, whatever, implement the Virtio functions, and send all this information and communication to the user space. From that place and on, it's the adapter, the application that takes the role to deliver them to the VIOS user devices. Now, the adapter doesn't play a big role on the data exchange, just it's responsible to deliver notification between driver and VIOS user devices, so it doesn't add any overhead. We are going to see briefly the two components that we talked about and which the technologies and the mechanisms that are used. Nothing special. As we said, the driver implements Virtio protocol functions, and then implement some system calls in order to interface with the user space components, the adapter and the device, event FDs to notify them for new data to be exchanged, and mmap handlers. So in a way to bring the data from the kernel to the user space without the need of a copy. Again, the adapter just implements the VIOS user protocol, which is the main part of it, in order to talk and communicate with the VIOS user devices, whatever it is. This is done from VIOS via Unix sockets and event FDs, again for the notification. Now on the other side, for the driver side, we have system calls and event FDs. These are technical details, but I want to focus a bit more on how this technology actually works. What's the workflow? How is the initialization process and how data are exchanged? Now we have two main parts, let's say, to how this system is initialized and the data are exchanged. We have the control plane and the data plane. So Virtual-Loopback starts by defining the control plane, and as soon as this is ready, we start with the data exchange later on, which is based on the shared memory mapping mechanism. Now the control plane, a few steps about it just to be sure that we are into that, and then we will move on. We're starting by running the VIOS user device, which creates a socket. With the adapter, we provide us an argument. This socket connects to that, and they do a basic exchange of VirtIO information, features, the VirtIO device ID, the number of queues, things like this. Later on, all this information from the adapter needs to be communicated to the kernel space, to our driver, basically. So via the system calls, again, it writes the features, it writes the device ID, the most important, and then the Virtual-Loopback transport knows which device to register on the VirtIO subsystem, and at the same time to start the new transport driver. We have a small initialization process into the kernel about the VirtIO. When the driver is ready, acknowledges the features, and then we need to lastly to notify the adapter that the acknowledged features are these ones. The adapter reads them and provides them lastly to the VIOS user device, and then we are ready to exchange any data. All the system is up to date. How is this data plane? What's the data plane and how we exchange actually data? There are two main key points on that. The key points is that we first need to have access to the V-rings. The V-rings, it's a data structure in the kernel used by and defined by the VirtIO protocol, and there are saved the scalar gated lists, just simply physical addresses of buffers into the host memory space, which holds the data. They hold the data. So first thing is to have access on this area, and then we have a second problem, let's say, that we need to translate the physical addresses that we read into this array structure and translate them so we know where the data actually is and get them. This is done in a three-step process. That was basically what was implemented in the beta version. We will go through that a little bit later, and we will talk about the current status. So currently what's going on? The driver has already shared the memory, the V-rings, let's say. So it tries to communicate to the device has already access to the V-rings. It reads a physical address. Now it wants to request this physical address to get a pointer or a virtual address to that space. It does that via an IOCTL to the driver. The driver, if it has seen this request again, immediately returns the address to the IOCTL, otherwise returns 0. Then the device knows that, okay, this is my first time that I'm trying to access this memory. That's called a map function. The map handler into the kernel space handles this request, finds and insert this specific page to the user space, basically. This is what's going on. This is done with remap pfn range function. And this is basically what I'm describing here, that the last step is the return of the map call, and from then on the device has a virtual address to the data. A bit about the history and the current status now. We have done in the past the alpha version. That was our first release. The first release basically introduced the transport, the driver basically, the adapter, which is the user space component, and a demo for the VIOS user RNG, which is the random number generator under the VIOS user protocol. And then we provided a demo, and that was a proof of work that this technology can actually have a place into the kernel. Then with the beta version, we tried to add a few more devices which were more important, let's say, the VirtIO block and the VirtIO input, some more automotive related devices. So as a feature at this release, we also needed to add multi-queue support for BLK and input, and the exchange of the configuration of these devices. The last step that we are right now and still ongoing is the Delta release. In the Delta release, we focus more to update the memory mapping mechanism, which is what I presented you before, the three-step process, and the notification mechanism. About the notification mechanism, it's not so interesting, so we're not going to focus so much right now. Let's see only the data-related stuff. So these optimizations, as we said, it's important here to note that this is the benchmarks that we are going to see and the mechanism that I'm going to present you. It's the first revision of this idea and design. So, just to make a connection that, to what we have seen before, the access to the V-rings, to the first data structure, still is the same. We call the mmap and we get access to the data, not to the data, to this data structure. Then we have the same problem, how we translate these physical addresses in a faster way, not with a dynamic mapping mechanism, which is costly when you do it all again and again. So at that point, we actually implemented a new memory mapping mechanism, which is based on page fault. What that means, we will see in the next slide. It's basically, I need first to tell you that we still need to do something during the initialization process, really briefly, to not make you tired. It's that we needed to make the device, the VIOS user device, to call repeatedly mmap, to do repeated mmap calls to the driver in order to obtain all machine physical memory. Now, this is not actually true because it doesn't have access to the whole machine physical memory, and there are security checks that are done into the driver. But what's really important is that the driver records all these requests and does a simple mapping that I have a request about this physical address and I return this virtual address, and what was the size of this request. Let's say, for example, a brief example is that the device has requested the physical address 10 with and 10 blocks of 4K, something like this. Last step is to assign a page fault handler and then return the call of the mmap. So now, the whole logic plays here that when the VIOS user actually tries to access the data, a page fault comes to the kernel into our driver. Our driver needs to shuffle a bit his records and see that, okay, this fault virtual address is corresponding to the mmap request, let's say n for convenience. The request n, as we said, it has three attributes: virtual base address, size, base physical address. By that knowledge, we can easily calculate that the virtual address request that trying to be accessed, the default virtual address, is equals to the virt base plus an offset, which we can understand in case of the physical address, it is the physical address plus the same offset. That's the whole calculation, nothing special. I might not be much clear. Please ask me later during the questions session. So last step, now that we have found out which physical address we want to exchange to the user space, just to insert it, nothing more. And this goes on every time that the VIOS user device tries to access a new virtual address that we have not inserted the specific page to the user space. Now, some competitive technologies that we are going to see and benchmarks that we run between them and Virtual-Loopback. Now, in case of the block and network devices, there is another one solution which we are aware of. It's VDUs, means VDPA, device in user space. It's an open source solution. It has been merged into the kernel already since the version 5.15. It has, as Virtual-Loopback, it has already not two only, but a kernel component and a user space component. The user space component has been, again, added into the Chemo project. Some brief difference between the two technologies is that VDUs doesn't support zero copy. It's not based in zero copy principle. It's based in a bouncing buffer mechanism, which copies the data from the user space to from the kernel space to the user space. Supports Virtio Net, which is important, Virtio BLK, but does not support Virtio input and RNG. Now a small overview about this technology, nothing special. It's that the VIT uses emerging approach for providing software-defined storage and network services to virtual machines, as QEMU did in the past, and still does basically, and container workloads. The whole logic about this technology, or the biggest part of the logic, is contained in the VDPA subsystem into the kernel. Now, if we see a bit into the picture, which has a lot of things to be honest, there is the Virtio VDPA, part of the VDPA bus, and a whole big component which is called VidUse module. These two combined, it's a comparison to Virtio driver that we have built. The logic, not the implementation, but it is the same logic. They are trying to bridge, to take all the communication from the Virtio drivers and forward them to the user space, which there is another application called VidUse VidDaemon, compared to our application, which is the Virtio adapter. Now, a small comparison benchmark. We ran some comparison benchmarks between the two technologies. I first want to show you a bit the environments and the parameters, the tools and the parameters that we used. We ran them in a server, an x86 machine with 16 gigabytes of RAM and 32 cores. The tool used for this benchmark was FIO. Briefly, to not describe all the parameters in detail, we did sequential read and write operations with direct flag enabled or disabled, block sizes of 4K, 64K, and 1 megabyte. I know that 1 megabyte is a bit big for a block size, but we did that because we see that in both technologies the performance was increasing while we were doing this increasement to the block size. And the runtime was about 90 seconds to more than 1 minute, less than 2, to get all the extreme cases and have a trustable average. Now, small comment on that, about the Virtio queues that we used and the configuration. We decided to use a small queue, basically to take these numbers, different configuration, and try to identify which are the differences in the behavior of both of the devices, of the technologies. We choose a small queue of 128 bytes, one big queue of 1024, and both scenarios of single queue and a multi-queue with 8 queues. Now these are the results. In the single queue scenario, we see that Virtual-Loopback outperforms VidUse 4 out of 6 cases. We see that VidUse actually wants one case with 4 kilobytes of block size and 64. So we can say that in the no, this is not true. In 1 gigabyte case, 1 megabyte case. But in any case, just to say into the content, Virtual-Loopback outperforms 4 out of 6 in the single queue scenario. In the multi-queue scenario, we see more equal behavior, but the best numbers are being taken from VidUse. All of the cases that VidUse has win in this competition, let's say, it's when the direct flag is enabled, which seems to use in a better way than Virtual-Loopback at that moment. Now, that's a few comments that we have already said, but let's sum up. It's that Virtual-Loopback seems to have a slightly better performance into the single queue scenario. VidUse has an advantage into the multi-queue scenario. Additional benefits, as we have already discussed a bit through the whole talk till now, it's that the Virtual-Loopback technology has zero copy principle. It's based that it doesn't do any copies to the user space. Supports Virtio input and RNG. Now, a few proposed optimization future work that we are going to reference later again into the slides. It's that it seems that we can increase a bit the performance by updating this page fault mechanism, the memory mapping mechanism. This can be done just for each page fault that is coming to insert multiple pages that we know that most probably the user space is going to use, read or write. In this way, we'll reduce the number of page faults. Probably it will make a bit better even to the cast misses that they are happening. Proposed features about the 2023 AGL. The first proposal is to add additional devices, Virtio devices, into this design. For example, Virtio CAN, Virtio Net, sound, camera, as much as more automotive related devices. Additional to that, to have some more features. For example, multi-queue device support, which means that multiple instances of the adapter, the user space application, can use the same transport driver for multiple devices, which means that you can have Virtio Net, Virtio RNG, Virtio input at the same time without need to use different drivers and etc. The next is to enable Virtio into AWS to support the migration from an automotive embedded device as it is the ArcRM3 to the Amazon cloud. Performance optimizations, we have already talked about it. It's to update the memory mapping mechanism that we believe is going to show a big impact into the previous presented results. Just to sum up a bit the whole discussion, and then we are over, it's that Virtio Delta release provides a fast and reliable solution as a hardware abstraction layer between the Virtio drivers and the VIOS user devices or other user space emulated devices. It is based on zero copy principle. It has done no modification of Virtio source code, and there are some few modifications depending on the version specifically about the VIOS user library, which we believe in future updates this can be totally eliminated. Alternative solution as VIOS seems to have comparable results, but they do not support the input and RNG devices until now. And there is, as we already discussed, big room for optimization and scalability, its capability for more Virtio devices. Now, more information about this design and details you can find into the Virtuo-Loopback design document found in the following address. Thank you all for your attention. I was really happy to present you the Virtuo-Loopback design. I'm open to any questions of the audience.